Start the stream. And we're back.
Okay, cool.
We'll just once again wait for everybody to settle down. It just seems so wasteful. I think that's the problem with rockets. They just seem like you're lighting something on fire to get to space. To do this
You
thing
are.
to and then also like setting poison on fire and letting poison into the atmosphere, and then you're smashing up your poison bucket into the Earth's atmosphere. That all just seems wrong, and I think that's why these alternative methods of getting around are so intriguing on our brains. So I don't blame people. Hey everybody, we're back. We did it. We made it.
We did. I like it. People like deja vu. Yes.
All over
yes.
again.
They had the links ready. Oh, I closed Audible, not Audible, Audacity. I need a new Audacity.
Ben Kayla notes, I'm lighting poison on fire when I drove to the grocery store. It's true. But at least you're not taking your poison bucket and smashing it up when you return from your trip to the grocery store. Ben Appleby, methane isn't poison. Good point. Good point. It's possible that human beings make methane inside them. And the way the BFR is going to do that by having a big factory that converts electricity to methane is pretty exciting.
And I think it's important to remember, though, that methane in large quantities really will make you want to die.
You mean to breathe it or to produce
well,
it?
Methane itself is smellless. It's other components that get added to natural gas that smell, as well as ancillary compounds from the bacteria in our guts. This is why not all gaseous emissions smell the same.
Right.
But methane can displace oxygen in a room. So you don't want too much of it if you like to breathe. And I think you like to breathe. I think you're kind of addicted to liking to breathe.
I'm for breathing.
Yeah.
Brooke Mulligata is asking, have you done an episode on the EM drive before? No, and we probably won't unless it...
That whole facts-based thing?
Yeah, until it actually works. If it works, we will do 2 episodes. 1, the EM drive is exciting. 2, everything we knew about physics is wrong. We'll do those 2 episodes and go from there. Because unfortunately, we heard a lot of interesting things about it, but same thing with the Alcubierre drive, both of those fundamentally violate the laws of physics as we understand them. So it's a tall order to say, hey, we've got an engine that also throws physics out the window. So anyway, that's all we're waiting for. We're just waiting for more tests. And
expanding physics is welcome. It's the throwing out of the physics that's the problem.
Hey, no. If you can throw out physics, congratulations, you did it. Good job, right? Right on, Einstein.
It's the if you can do it.
If you can do it, that's all. Right. That's by all means. We can't wait for these stupid physics that keep us from traveling around the universe on our warp drives. We can't wait for that to be overturned. I want a Stargate, please.
Yes.
Right?
Yes.
I want to be able to just walk through a door and show up on another world. That's what I want. But I also know that that's not going to happen.
With our current understanding of physics.
With our current understanding of physics, exactly. Which is quite a lot. So... Oh, well, yeah. Bill Sugden says Alcubierre drives will work with negative energy. Right. So all you need is negative energy, which is the law broken. So anyway, don't get me wrong. I am as excited about all of the things that science fiction told me as anybody. But I also just, I need to manage my own expectations. I talked about an air-breathing electric thruster in the last episode. Super
You did.
exciting. So great. Here I am.
I love how sometimes we can just see your brain stop.
Like I'm reading. I'm reading at the same time. All right. Well, why don't we get ready and do this episode? Save up all your cool questions. We'll have more of a conversation about this kind of stuff at the end of this episode, and we'll go from there.
Okay. Are we ready to
I'm ready to press record.
I'm pressing record. It is recording.
All right. Here we go. Hello, Chad. Just in case we forgot to say hello to you. Astronomy Cast, episode 483, Stopping in Space. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos. We help you understand not only what we know, but how we know what we know. I'm Fraser, Cain, publisher of Universe Today. With me, as always, Dr. Pamela, the Director of Technology and Citizen Science at the Astronomical Society of the Pacific, and the Director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. And I just realized as you introduced us, I should remind everyone while you're listening to this, if you're not like at the gym exercising or otherwise moving around doing useful, productive things, you should go online to cosmoquest.org and do citizen science. We just upgraded all of our mapping interfaces. You can help us do new science with Mercury mappers, Mars mappers. There's the Moon and Vesta waiting for your inputs. So, hey, if you're looking for something to do while you listen or watch this show, go to cosmoquest.org and do science.
I think it's more than just looking for something to do. If you want to make a meaningful contribution to our scientific understanding of the universe, if you want to participate and be part of the science that's getting done around this solar system, go to CosmoQuest. And
thank you.
And help out. It matters.
And I will personally be very, very grateful.
Perfect. You got that? Personally grateful. It's one thing to get from Earth to space, but sometimes you want to do just the opposite. You want to get into orbit or touch down gently on the surface of a planet and explore it. How do spacecraft stop? And what does that even mean when everything is orbiting? And we're not just going to talk about stopping. We're going to talk about transfer orbits and slingshots and all kinds of stuff. All right. Where shall we start? Well, let's talk about this concept of stopping. So we've spent a whole bunch of episodes now talking about going and different methods of going and why going is so hard. And now let's talk about stopping, because it turns out stopping is also hard.
Yeah, so you get yourself going, you're whipping around the planet 90 times a minute or so if you're on the International Space Station. You might be going faster, you might be slower. Geosynchronous orbit, you're going around every 24 hours, but you're so high up, you're still booking it through space. And with these large velocities, if you want to get back down to the surface, you have to somehow reduce your velocity. Otherwise, you're just going to stay up forever.
And, we talked about how difficult it is. Like when you go into orbit around the Earth, you're going from, say, into low Earth orbit, you're going from 0 to 28,000 kilometers per hour around and around and around the Earth. That is orbit. That's the trick. So you have to then, if you want to return to Earth, say you're sitting on the International Space Station, you want to return to Earth, you need to go from 28,000 kilometers per hour to 0.
Well, it's not quite 0, to be fair, because if you're at the equator of the planet, you're going around at 1,000 miles per hour.
Good point.
But there's still a whole lot of reduction between those two different speeds. And I'm using the word speed because your direction's constantly changing, velocity. Words, they're hard. And in this case, speed means how fast you're moving through space without care of direction. And velocity has a direction that is constantly changing if you're in an orbit. So don't screw these words up. Your local physics teacher will want to punch you.
Speaking of, you mentioned that you go 90 times a minute around the Earth. I think what you meant to say is you go once around the Earth every 90 minutes.
I did. Yes. Words, they're hard.
Yes, clearly, even for you.
So So here's the thing. You're up there, or worse yet, you're a spacecraft approaching Mars and you want to be on Mars, not
Well,
approaching Mars and
let's start
flying
with Earth.
past it.
Let's start with Earth first, just because
Okay,
it's so much easier than Mars, and we'll get to Mars because it's
it's true.
harder on so many levels. Well, let's just start with Earth briefly.
Okay, so with the Earth, stage one is to throw yourself at the atmosphere. It's
I
true.
know, I know it. I love it. I love it. You just throw yourself in the atmosphere.
And the way you throw yourself at the atmosphere is you have to reduce your orbital velocity, which if you're in a low enough orbit, you can just wait long enough. The Chinese space station is currently taking this particular approach to coming out of orbit. If you're an astronaut, you may lack that patience. You want to get home and experience gravity and tasty food. And in order to get back down, you fire engines to slow your forward speed, to slow your orbital velocity. And when this happens, you go from an orbit that will keep taking you around the planet to an orbit that intersects with the surface of the planet.
One thing that's really interesting, and I sort of discovered this doing a recent video, is that, like, say back with the space shuttle, they would fire their retro thrusters, and the amount of difference in orbital speed that they would do is actually very slight. Space shuttle would
Yes.
only need, I think it was a little faster than a fastball pitcher throws a fastball. So just a couple of 100 kilometers per hour in change in velocity was all the space shuttle needed to set it onto an orbit that would bring it back through that, as you said, begin the process of throwing yourself at the atmosphere.
And this is why they don't need to have massive orbits to get, not massive orbits, sorry, Chad. And this is why they don't need to have massive engines to get out of orbit. You can use those little tiny thrusters that they had on the shuttle. You can use the little tiny thrusters they have on the current Soyuz capsules. Get that little tiny delta V and then let the atmosphere do most of the rest. Now, most is the key word here. Whether you're the space shuttle or the Soyuz capsule, you want to hit that atmosphere at just the right angle to make sure that you're braking with the largest surface of your spacecraft that hopefully has a heat shield on it. And it's taking the brunt of the force. In this case, it's a normal force being exerted by the atmosphere, and you're going through the atmosphere. You're getting frictional heating as you push all that atmosphere out of the way. The air around you is actually getting ionized. It looks like it's on fire. You feel like you're going to die, is what I've heard. And this gets you significantly slowed down. This gets you down to the terminal velocity of whatever kind of thing you're in. Now, the problem is if you hit the planet at your terminal velocity, that probably isn't healthy for humans or content inside the rocket.
And, just on a bit of a somber note, of course, there was the return of the Columbia, the space shuttle Columbia, that was performing this maneuver. There was a crack in one of its wings that hot gases got into from the atmosphere as it was performing this deceleration maneuver, and it was enough to tear the orbiter apart, and all 7 crew members were lost. That has, it is a very dangerous time. When you're going around and around out in orbit, you're not going to run into anything unless there's some space debris. But that hasn't caused an issue so far for astronauts. It's that return flight is very, very dangerous and quite scary. And you got to get that angle, as you mentioned. You got to have that angle of your spaceship exactly right. When you've got a capsule, whether you've got a glider, you've got to bleed off that velocity right, and you've got to be able to make that transition from thing that tried to throw itself at the atmosphere to thing that is able to gently return to Earth. And that's a tough transition to make.
And if you get the angle wrong, you're either going to get through the atmosphere okay, but be at far too high of a velocity, or you're going to end up tumbling and lose control. Both these things are bad and lead to death, which is not optimal. Um, I'm trying to add humor to this because it's such a black topic. And with the Columbia, the heat that got into the wing was sufficient to damage the aluminum structure. We're talking the aluminum got melted
Yeah.
in parts, and this is extraordinarily high heat. So those heat shields, they really matter, and you have to get through just right, or you lose control or you come in too fast.
And there's no alternative. Like if, and we'll talk about this in a second here, but if there was no atmosphere, then if you wanted to land, say, on an airless Earth, or let's say the moon, you just have to reverse the maneuver that you did that allowed you to take off in the first place. But you can't do that with any place that has an atmosphere because you've got to deal with this atmosphere. It's an advantage. You don't need a lot of energy. You've got lots of energy. You need to get rid of that energy. But the disadvantage is you you have to deal with the tremendous forces, and there's kind of no way to go around it. I think of it like going down rapids. Like you're in a boat and you're going down a set of rapids, and you can't, once you commit yourself to the rapids, you can't get off, you can't make it stop, and you have to just ride it down to the bottom. And if you watch like Apollo 13, they have a great sequence where they're coming back through the atmosphere, and it's quite suspenseful. And that is what it's like for people trying to interact with the astronauts as they're coming back through the atmosphere.
And you lose communications with your capsule at this point because all of the ionizing radiation blocks out radio signals. So there's this point where you don't have any communications, and it looks like the world outside your capsule is on fire due to all of the ionization that's going on. And you just have to suck it up and
Yeah. Hope
trust.
and trust in the engineering and trust in the technology. All right, so I stopped you before you went too deep into why Mars, because Mars is even worse. So let's talk about what the.
But we haven't really stopped. We've just hit terminal
Oh, right.
velocity.
You want to actually land now? Okay, sure. Go ahead.
So so once you make it through the atmosphere, you're still going at the terminal velocity of your vehicle. This is the velocity that you fall at based strictly on the shape of what you are. A feather has a much lower terminal velocity than a brick, for instance. Now, with the space shuttle, in order to slow down the rest of the way, they actually did these amazing S turns. So they would bank back and forth, just like you and I have probably both done skiing to slow down. You lose all of your energy going through these turns and dropping it with the friction at the curve.
That's a great analogy. I really like that. That it's just
It's
like how when you're skiing. That really helps understand it.
and it was actually, I learned about the space shuttle before I learned about skiing, so I learned that analogy in the opposite direction the first time.
Right.
Have I mentioned I was a weird child? Uh, so with a capsule, you don't exactly have the capacity to do S turns. So here they have to have parachutes, and they often have a first parachute that gets them down to one speed, and then they let off another set of parachutes that are much bigger and would pretty much blow apart with the initial blast if you didn't have a first parachute. So it's a staged process. Use the atmosphere, then use parachutes. Even the space shuttle had a final parachute, in this case, a drag chute that it deployed to break when it hit that runway.
Hmm. And it is still like the Soyuz capsules, the Russian Soyuz. They still use that parachute system. They land those capsules in the steppes of Kazakhstan. It's a rough landing. Now SpaceX, of course, it's time for us to say nice things about SpaceX. They're not necessarily coming back from. They haven't cracked doing a powered, landing from orbit, but you can kind of see the direction that this is going with the way the booster rockets go.
And here we start to get to the technology that also gets used in part on Mars, which is the idea of uh, just land on those same engines that you took off on and fire them to slow yourself down. It's what we all watched in the Jetsons growing up, and now it's starting to become our modern reality.
All right, now can we talk about Mars?
Yes,
Okay.
yes. Now we can talk about Mars.
It's
So
so why is Mars so much worse than Earth? I mean, Mars eats spacecraft for breakfast. What's going on?
well, it eats spacecraft for breakfast for many different reasons. One of the problems that we have that luckily doesn't seem to be the primary reason it eats spacecraft. The primary reason seems to be human issues. Uh, but Mars, it doesn't have enough atmosphere to let atmospheric braking get very far, but it has so much gravity that using retro rockets just doesn't quite work for the entire thing. So you have to have this combined approach of first drop your speed using what atmosphere you can, and then figure out how do I get the rest of the way there. And early on, there were fabulous solutions in the modern Mars exploration era, so the late 90s forward, where we tried things like Pathfinder was a bouncy ball,
Mm-hmm.
and that was fabulous. It was the we shall simply make this thing very rigorous, and we shall drop it with airbags, and the airbags will get rid of the energy because it's not a fully elastic collision. So after a number of bounces and a bit of rolling, you now have a no longer moving spacecraft that presumably like a wibble wobble, weeble wobble, like, sorry, Chad, presumably like a weeble wobble, it always ends up standing upright and opens up and out deploys your spacecraft.
But the size of those rovers was literally the maximum size you can use that technique. So they had to use something a little more complicated for the Curiosity, which is more like the size of a mini, like it's a much larger vehicle. They couldn't use that bouncy ball.
And this is where we get the 7 minutes of terror. This was another combined approach. So, first it did aero braking, then it did parachutes, then it did retro rockets, but they didn't want to disturb the area around where they were going to land the Curiosity. So they dropped the Curiosity on a tether with retro rockets firing above it and off to the sides in this crazy sky crane approach. And then they landed the retro rocket part, or dropped it, as the case may be, a little bit off to the side.
And a lot of the spacecraft that have been sent to Mars, it's this orbital entry landing approach that's gotten them killed. With again, SpaceX, they're talking about the BFR and the plans for the BFR to go to Mars. They're shifting back to a powered landing because now the payloads are too heavy. You can't use really much of a parachute. You can try to use as much of the atmosphere to brake as you can, but you can't use a sky crane. You can't put the BFR in a bouncy ball. You've got to land with rockets.
And the past several years, it's been crazy watching NASA and other groups try and figure out how to engineer bigger and bigger parachutes. And they're just not getting it to happen. So, this is really a more feasible direction in a lot of ways. And what kind of amazes me is this is exactly what we saw in The Martian, where you have that rocket that landed and then is waiting, primed, sitting there, ready to go in the same orientation that it landed in.
Yeah,
This
and you
is new.
yeah, absolutely. And back to this idea of like being able to build your fuel on site and be able to go from there. Uh, let's talk about some other places that we have landed on. Like what about Venus? The Soviets sent their trusty spacecraft onto Venus and they made it down to the surface.
And then they melted.
Yes. Well, you can't go to Venus without
Venus,
melting.
well, yeah, Venus isn't really a problem to stop on. The problem is landing where you intend to, because the atmosphere is so thick, it buffets you so much. It has really high winds, but it will slow you down. And there are lots of really cool ideas for how to get to the surface safely. It's just staying on the surface without melting that is really the issue.
Yeah. And then the other place that I think has been sort of a fascinating landing site is Titan.
Titan, we have landed there.
And it's like the
Again,
perfect
super
world.
thick.
Yeah.
Yes.
It's like the perfect place to land.
And on every possible front, because you do have to worry about landing in fluid. They do have lakes, Great Lakes on Titan, so be prepared to float. But the atmosphere is thick enough that if you attached Icarus style wings to you and I, we could happily fly around in the atmosphere if we had a spacesuit to allow us to breathe.
But well, you wouldn't need a pressure suit.
No, you just need protection from radiation and protection from lack of oxygen
And cold.
and cold.
Yeah.
But you could fly.
Yeah. But so the
And
gravity's not pulling you down as harshly. The atmosphere is much thicker than we have here on Earth. It is the perfect, safest place you could try to attempt an orbital reentry.
and the only reason you want the bouncy ball airbags is if you land in a lake. So don't land in a
Right.
lake.
Have a boat.
Have a boat.
Yeah. And then what about the moon? I mean, we've all played our lunar landing game. How does that work?
Moon, it's another one of these low gravity environments. And here we nailed it on using rockets to do a powered landing. Just like we've seen the SpaceX Falcon 9s land, that's the same technology, just a whole lot more advanced as what they had that they were using with joysticks and buttons to land on the lunar surface. We were able to do it in the 1960s and early 70s with the lunar landers with such low tech because there was such low gravity. And that means the challenge is much less.
And then, sort of as a connection to that, think about what it's like to try and land on places like Rosetta. Poor Philae had was on 67P when the Rosetta mission. Philae had a really hard time, and now we're looking at the OSIRIS-REx mission, which is going to be doing something similar. This is the Hayabusa 2 mission, which is going to be bringing back a sample from an asteroid as well. Why are asteroids so difficult to get to zero?
Asteroids and comets have two different problems that you have to contend with. One is those suckers are rotating. And so you have to figure out how to match that speed that the surface is moving at, which may be a faster velocity than the one you want to stay in orbit. So you're trying to not accelerate away to match the speed of the surface. It gets tricky. The reason this is so tricky also is it doesn't have sufficient gravity to really pull you down. Philae felt the same way a piece of paper on the planet Earth feels when it comes to weight. So Philae had to harpoon itself into the surface to hold on, and this was where it didn't exactly succeed and bounced around a bit before it finally settled. Now,
On its
because
side.
on its side, and because it did have essentially equivalent weight to a piece of paper on Earth, it did settle to the surface. There was gravity. It just wasn't a lot. And if you're trying to land on a rotating chunk of rock, you have to match the orbital velocity, you have to match the surface's velocity, and you may only have a comparative weight of how a couple pieces of paper feel.
Mm-hmm. I mean, from what I understand, Philae didn't bounce as much as the researchers were expecting, but its retrothrusters failed, its harpoons failed, and so it just wasn't able to use the two devices that it was supposed to have to be able to make this landing. And part of the problem is that spacecraft was so far away that you can't in real time adapt to the issues that are going on. And this is what we're going to see time and time again as we explore the outer solar system, as we try, as we try to land things on Mars. You talk about the 7 minutes of terror. When Curiosity was making its descent through the Martian atmosphere, it was 15 minutes away from Earth or longer. And so people on Earth had no way to stop it, change it, fix it, tell it to do something smarter. They had to just follow the programming and couldn't adapt. And that's one of the last reasons why it kind of makes sense to have humans do some of this stuff, is that they can be there and they can adapt, and as the conditions change.
And with OSIRIS-REx, we're somewhat hopeful that the way the mission has been set up, this will be a fairly straightforward approach. At grocery stores or carnivals, you may have seen that grabby game where you have the claw that drops down, grabs a toy and drops it in a bin if you do it right, drops down and grabs nothing and drops nothing in a bin if you do it wrong. Well, this is a very similar approach to what OSIRIS-REx is going to do. It's going to come in and try and grab a rock and bounce away. This is a fairly simple process. The only trick is going to be finding a rock and grabbing it quickly. And if you want to be one of the people who potentially helps with this, go to cosmoquest.org. Prove yourself as a crater marker, because we are going to be using rock markers later to find rocks for OSIRIS-REx.
Oh, that's cool. Arjone in the chat, as we're doing this live show, is noting, I think this is a great point, is that it's now believed that the surface of Enceladus and Europa are actually too soft to even land on. That it could be that they're actually quite squishy, and because of the low gravity and because of sort of what this material might be, that it might be too slushy, and that any lander might sink into it. So it's it's not even about trying to get down to the surface, but it could very well be that there's no hard surface for you to get on. So it's like going back to, like, maybe you need to take a boat, maybe you need to take great big floppy snowshoes on your spacecraft. And this was one of the concerns that people had about the moon back in the day. Before they were able to actually land on the moon, they weren't sure that it was even going to be possible.
They thought there were meters upon meters of lunar dust potentially, or inches upon inches, which would still be enough that they couldn't free their spacecraft later. But luckily, it turned out they were wrong.
Yeah.
And so they were fine.
And so let's hope they're wrong about Enceladus and Europa as well.
It's true.
But the bottom line is that really getting off Earth is really only half of your challenge. Landing and wherever it is that you want to go, arriving at your destination is the other half, and as complicated as required. All right, well, Pamela, I think we've filled up this episode. We will. I'm not sure whether we're done. We wanted to talk about some orbital maneuvers, maybe some rendezvous docking. Transfers, some things like that. So maybe one more episode.
One more.
Yeah, we'll see how this goes. Too much fun. I'm having too much fun with all of this spaceflight stuff. All right, we'll talk to you next week, Pamela.
Sounds great, Fraser. And
there, Noel, I answered your question, which is it just turned into another show. So this is 483.
Thank you.
Yeah, we're talking about like on-orbit construction, docking, refueling, what happened with Hubble, trying to sort of get to and repair Hubble, how the Soyuz capsules boost the space station, or things like that. So I think there's some other interesting conversations to be had.
Yes.
Actually, maybe just that's an episode, and then talking about Hohmann transfers and gravity assists, etc. Is a whole other one as well. So maybe two. Feels like there might be two there.
Maybe do one on all the transfers and another one on refueling and docking, so that's the technological side of
Yeah,
it.
talk about various kinds of orbits. Those, yeah, and then talk about, and then another episode about docking and refueling and construction and stuff. Because one of the questions people always want to know is like, when will we start to do orbital? Like, why fire it all off in one launch? Why not fire up one rocket, then refuel it, and then go? So there's a lot of sort of great ideas with that. And of course, once again, we got to talk about Musk, how the BFR and the BFS will have a will be able to refuel, right? They'll mate end to end and
Yeah.
totally be able to refuel each other. So it's pretty fascinating. And Noel Rippenthal saying free return trajectory. That's a great one. We can talk a bit about like the interplanetary highway, how there's these free trajectories from place to place. Lagrange points a bit. But anyway, I think that'll be interesting. Just sort of the interesting ways you can go. Who's binging? Glancaster's binging. Good. Right on. It used to be, it was hilarious. When we first started doing the show, people would be like, oh, why don't you... I now have to wait. I've caught up. I've listened to all 20 episodes, and now I'm caught up. And when are you going to make more shows? Nobody ever says that anymore.
No, no longer a thing.
No,
No.
no, we're done. You want more shows? You got 483 to listen to. Furio and Acro ones. Will there be one on impractical drives?
I
Improbable drives?
that's exactly where my brain
Yeah, me
went
too.
too.
The-
I think that's called my Twitch feed when I'm discussing science fiction.
Is that what, like, everyone wants to ask you?
So like right now, we're going through the book Off on a Comet by Jules Verne and discussing the weird fiction in that. We've talked about Star Wars before, so
It's
yeah.
so funny. I don't know if I've mentioned this, but I've just become this sort of jaded realist now of the sci-fi, of the YouTube science or the space explainer group. So there's clearly these phases that people go through when they first, they read a bunch of science fiction and they've watched all their Star Trek and Star Wars, and they're super excited about these ideas, and they hear like, oh, there's and then there's space elevators and all kinds of really cool ideas, and I wish they're real, and how long till they're real, and then after a while, and like, when can we send missions to other places, and now I've just become the kind of the grumpy realist in this field, and it's hilarious because I'm the wide-eyed optimist. I'm the one who's just like, and you're
I'm the
one
sarcastic curmudgeon.
and you're the sarcastic, and so I am becoming the curmudgeon as well. And it's pretty funny to see this next generation of wide-eyed optimists, who I'm assuming will become curmudgeons as well, because you just spend decade after decade waiting, for your dreams to happen, and it just never, just never happens. Like, even, man, like, so we just did this episode about artificial gravity and I've been doing a bunch of research, and how NASA has been attempting to research this for a long, long time. And, they've done some really interesting research on it. They know that you need about 0.2 Gs to be able to just even walk around. You need about 0.3 to be able to move around and do stuff. But Boeing has tested out this little gravitron that they found that you can go up to about 13 revolutions per minute and get used to it. You can become accustomed to it. And so we're not going to have this Space Station V or Space Station 5 from 2001. We're going to have this tiny little 4-meter radius centrifuge that you get into, and it spins you up at 1G, and you just spend a couple of hours every day in your little centrifuge. And you could fit this on a regular payload fairing. You could attach it to almost any spaceship and give artificial gravity for X hours a day. And for me, I'm like, that sounds great, right?
The only problem is trying to figure out how you don't accidentally spin up the rest of your spacecraft. So it needs to have a counter something to rotate in the exact opposite direction. Otherwise, really bad things will occur because
Yeah,
you
you
have
would.
now made a gyroscope.
Yes, and so you do need to sort of counteract the spin that this thing is doing. And one idea is that you balance them out. So you put one on the other one on either side, and so two astronauts can be in their little centrifuge at a time. But the part that I thought was great was, it's one thing to say, can what would it take for us to be able to have 1G? And you would, in fact, need, for us to be comfortable in 1G, you need a space station that's about 300 meters across. And
Yeah.
I did the math that it would take about 450 launches of the BFR to put that kind of mass into space, to build that space station, right? You would have to tie up the entire space industry for decades to build your big rotating space station. But if all you needed to do was have a place where people would not die, but they would be able to survive, it's actually a much smaller machine that's required. So anyway,
It's the difference between laying down and walking around.
yeah. Yeah, exactly. You would totally lay down, or maybe you'd be riding the bike while you'd be doing it. And so Uncle Bill Drew is saying the small radius spin is motion sickness as soon as you move your head. Yeah, absolutely. But what Boeing discovered was, if you put people in this for about a month, they stop getting so sick. So we can become accustomed to the gravitron is what they discovered.
But that month,
Oh, it would suck. It would suck, right? You would spin it up time after time after time until you would be at full speed, and then you would have to, because right now astronauts have to exercise, they have to ride their bike and do all kinds of stuff for
hours
hours,
upon
hours
hours.
and hours and
Yes.
hours every day. So you could have them be in gravity, and they could be riding their bicycle, and they would be fighting off nausea, but at least they wouldn't be suffering those various downsides of being in microgravity. The things that you can't fix with
Yes.
exercise. So so it's interesting, like that alone. Like, I would love to see one of these in space. Like, I don't need any more the 300-meter across space station. I need this tiny little spinning device.
I like Lancaster's idea of inflatable space habitats and just a cable connecting them. It's
Sure.
all good.
Yeah. Yep. And that idea has been proposed as well. And sort of this goes back to my capabilities driven space exploration, right? Let's try new things. Let's not say we're going to go to the moon, and then say we're going to go to the Mars, and then say we're going to go to an asteroid, and then come back around. Let's just try to do something just a tiny little bit more complicated in space every time.
And it really is amazing how your brain gets used to things. Gordon is pointing out that sailors get sea legs and then get land
Yeah.
sick when they get back to from long voyagers. And I know I personally, after a really long airplane flight, you get off the plane and then you feel like everything's constantly
Yep.
vibrating. Our brains are amazingly versatile
Yep.
in what feedback they can decide to completely erase and
Yeah.
then put back.
I am right. So when I was a kid, when I grew up, I lived on this island, and we had to take two ferries and three buses to go to school every day. It took me an hour and a half every day to get to school, and we would go whether there was big storms or not, in taking this ferry boat, and it could be significant. And so I am essentially immune to motion sickness. I don't get motion sickness ever. I could read forever. I could read
Yeah.
on a boat, no problem. And I haven't been motion sick since I can remember. And so you can get accustomed to motion sickness. And so that's what they're doing, is saying, hey, let's not try to make it comfortable for space tourists. Let's see if an astronaut is willing to handle that kind of punishment, to make sure that they don't lose their vision, they don't have the vision problems, they don't get the fluid readjustment in their body, that they don't have these problems with their system of balance. So
And the answer is yes. Yes, they are willing to do
yeah,
that.
they're willing to do that, and much, much, much scarier
It's
things.
true.
Yeah. So I think that's what I would love to see this experiment run.
The movie The Right Stuff, it's a classic. If you haven't watched it, go watch it.
Yeah.
What they put these early astronauts through, good Lord. It really shows
Yeah.
what these pioneers were willing to do to open that new frontier.
It is pretty fascinating to see. I don't know if you like, if you read Endurance. I've got it behind me. This is the book by Scott Kelly. He comes
Yeah.
from that test pilot background. Same with his brother Mark Kelly, and the way that a test pilot, that was the path that you could become an astronaut, was you would,
Yep.
you would go to the Navy or the Air Force. You would go into this region of it where you'd be testing out new spacecraft, sorry, new aircraft, new techniques, and then that was your way to become a pilot astronaut. And so they have a mindset. They're human beings, but they understand that they're testing something at the very limits of how this works. So it's pretty fascinating stuff to see astronauts and how their brains work. I love talking to astronauts because they're so great. Every single
And
one of them. Right.
and they come in every personality type. There's this stereotype that a lot of people get of astronauts are these bigger than life, extroverted human beings who it's the test pilot mentality. But then there's some of them. I watched the most amazing conversation between Don Pettit and Babak Tvarshi, who's a National Geographic photographer and does amazing astrophotography. And Don was just like, I couldn't figure out how to get my exposures right. And they just had this very quiet, polite, and it was like wandering in and watching two introverts quietly nerd out about photography, and one of them did it from space.
Yeah.
It was awesome.
Yep. Yeah. Who was the? I mean, I got a chance to talk to one, right?
Yeah. Well, we both did when we were out in Ohio.
Oh, right. Yeah. Yeah,
Yes.
when we were out at that talk that we gave.
At
Yeah.
OSU with
Yeah.
Paul Matt Sutter.
Yeah, that was
Yeah.
really cool. Any questions? We've just been talking.
It's true.
Yeah.
We've been babbling to
Yeah.
one another.
Yeah. Any questions there? So BK Nesheim asks, what if you have a spacecraft with a wire between them? They both accelerate while they're spinning around each other. That would totally do the trick. If you could, stretch, say, take two BFRs, have them attached by a cable 300 meters long, set them spinning.
It's the dumbbell idea.
Yeah. But the problem is they are spinning 300 meters apart. You can't get from one to the other very easily. Once you're done and you want to put yourself back to a better orbital insertion orbit, you're going to have to get rid of all of that motion.
And the moment of inertia on a dumbbell makes it really unstable. You really do want that full ring to have a much more stable platform. Otherwise, just like bouncing around inside is going to totally screw up your entire space station.
Yeah.
You want to be able to play ping pong in your space station, as far as I'm concerned, and you could not do it with a barbell-shaped space station.
Because it would be wobbling too much?
You'd easily set up vibrations. The moment of inertia makes it much easier to set it spinning in a different axis than a disc is.
Right.
If you think about it, a disc has a preferred orientation. A barbell it can rotate about its center a whole bunch of different ways.
Right. John Drake is asking, when is the next show? Susy, do you know when the next show is?
No, she doesn't. Hold on. Let me pull up my calendar and we can estimate, because I'm only home for 3 days before I leave for Japan.
So
the 21st, if you're available on the 21st.
Probably. I'm not going anywhere until June. So
okay.
Yeah.
Then it will be on the 21st.
Okay. Perfect. Unless somebody wants me to do something before then, but right now I have no plans. And then July, Australia, September
Yes.
cruise, November, no, October. I think we've got a wedding to go to. So,
October, I'm going to Australia.
Arjun asks, does the ISS use small thrusters to compensate for occupant motion?
Yes.
Do they do? I mean, specifically for occupant motion, they just have
Well,
small thrusters to just manage its attitude, right?
they have accidentally set up oscillations where someone doing something has found the resonant frequency of the ISS and they've
Oh
had to
no.
damp down the system. So it's not that your every motion is counteracted. It's that they build up over time, and periodically you fire things to damp things back down.
Yeah. Do we have any plans for April Fool's Day?
It's
No.
Easter Sunday,
Is it?
and I have visions of there's going to be dad humor in those plastic Easter eggs to end all dad humor. I am so glad I'm not a little kid this year.
we, hey, what's wrong with dad humor? Um, we've done some in the past on Universe Today. Nancy and I came up with a bunch of schemes that we've done. We've had some good ideas. It's just, man, like one, I am so tired of April Fool's Day on the internet. Like I am sick of
Yes.
it. So
Yes.
sick of it. Like it's a minefield. It's people trying to get publicity for themselves. And so I just don't want to. I just can't participate. I can't bring myself to. And then the other thing is I'm so numb to trolls that I just don't want to even, like I'm not going to do an episode on Nibiru, and I'm not going to do an episode anything on flat or any of that stuff, right? Moon hoaxes and Tesla hoaxes and all that kind of stuff. Like I just want those.
I hide from the internet on
Yeah.
April Fool's Day, and this
Yeah.
year I'm actually going to be on airplanes all day, so it
Yeah.
works.
Yeah. But man, again, we're just two curmudgeons here
Yes.
on Astronomy Cast. So Bill Sugden asks, do we know if 1G is needed? Could we use less? So
We don't know yet.
Right. I mentioned that briefly that according to NASA, you need 0.2 G to just be able to walk. So if you don't have 0.2 G, you won't be able to walk around. If you have 0.3 G, you can walk and be able to operate equipment in your laboratory and things like that. But we don't know what is the minimum amount of gravity that we need to remain healthy. And there's something like 11 health problems that happen from microgravity, 8 of which can be handled by health and exercise, 3 of which can only be handled by gravity. And so we just don't know what is that minimum amount of gravity, and so experiments are needed. And there's been lots of ideas about testing on mice and things like that. One of the great things that happened with this whole year that Scott Kelly spent in space is he did a really great base level to see what it does to the human being, to the human body, to spend a whole year in space compared to his twin brother who was on Earth. And so now you could, for example, put a person into some kind of centrifuge, spin them at 30% gravity, and see if that helps with what happened. Maybe send Scott Kelly back. I'm sure he would. I don't know if he'd be up for it.
Now, I'm seeing people asking in the chat about the travel that we mentioned. So we should probably just be a little bit more specific because we're doing a bunch of public events that people will be able to join us for.
Mm-hmm.
So I don't know if I'm going to do a meetup while I'm in Israel. I'm letting Elad and Yov set my entire schedule and Yov's fabulous wife, Karen. So bother them if you're in Israel. While I'm in Japan, I'll be attending the Communicating Astronomy to the Public meeting in Fyoko.
What's the date for that?
I am going to be there. Whoa, I moved my calendar too much. I'm going to be there from Friday, March 23rd until April 1st. Then I'm going out. I don't have any more travel again until I go. Well, I have traveled, but not public travel. I'll be at Alcon this summer, so July 12th through the 15th. So if you're part of the Astronomical League, I'll be at their meeting. And then I will be at the Australian Skeptics meeting, which is the weekend of the 12th of October. And before that, I'll be in Melbourne doing as yet unplanned events, but Ed Brown and Lucas Randall are working on planning
Awesome.
that.
I'm probably going to be going to VidCon, which is from the 20th to the 23rd of June, which is down in LA. And then I'm going to be in Australia at Byron Bay on July the 7th and 8th. And we'll probably be hanging around that area. I might be talked into going down to Sydney, but we're probably going to go north from there through Brisbane and north of that. Apparently Australia is a big place.
Yes.
And then, of course, we've got the cruise that I'm doing with Dr. Paul Sutter, which is in September around the 10th to the 18th. Go to astrotours.co and you can see all of the upcoming trips. And then we've got Costa Rica in March. So, and that is our schedule so far. But as we know other events, we'll definitely post them. At some point, we should probably put a calendar where we show what we're doing. And so people can meet up with us. I love doing those kinds of meetups. It's just hard to kind of let people know and coordinate them. So, and then we've got the book coming out later on this year. And so I'm assuming David and I will be, doing some kind of road show to help promote the book. So,
you have a place here in St. Louis.
Right on. Then we're going to come to St. Louis. Maybe that's what we'll do. We'll just crash on people's couches and travel around the States. David's already a nonstop traveler, so he's probably an expert on this. All right, we should probably wrap up. We've reached the end of our hour. Thanks, everybody, for joining us. As always, I want to give a huge shout-out to the WSH crew. Go to wshcrew.space. They're the ones who are providing this chat that's down here, but they really are the community that surrounds and communicates with us. We've got a special Slack channel where we talk, and you can reach us. So it's free to join. Go to wshcrew.space, and you can be part of that community. All right. Thanks, everyone. We'll see you all at the 21st. See you, Pamela.
Bye-bye.